Okay, just a quick reminder about test number 5 on Thursday. Okay. We cover sections 4.6, which we did last week. This was about determinants and let's start recording. And the invertible matrix theorem. And we did 5.3. The topics that we need for test number 5, we did yesterday. Okay, so we did span and the null space of a matrix. So just remind you about those two things, which are kind of technical definitions here. Okay, so if V is a vector space which has a finite number of vectors, okay, V1, V2, V3. Those could be functions or could be matrices or could be just vectors. Okay. Then we say that W is in the span of V1, V2, V3 dot Vn if we can write W as a linear combination of those vectors. Okay. So if C1 V1 plus C2 V2 plus Cn Vn equal to W for some scalar C1, C2, C3 dot Cn. Okay. And not all of them need to be non-zero. There could be some zero scalars in there, that's fine. At the end of it, we should be able to represent this W as a combination of those vectors there. Okay. Which means that if W is in the span of these vectors, then this system of linear equations must be consistent. Okay. There could be a unique solution or infinitely many solutions that is not in our control, but if the system is not consistent, then the span is not possible. That is what the main theme of section 5.3 is, in addition to subspace, which we are not really covering as a mandatory topic. Okay, so this is one of the key things in 5.3. And the second thing was null space, which is nothing new. If you have done your homework in section 4.3 and 4.2, you know what null space is about. Okay, that is the solution to the matrix or solution to the system Ax equal to 0, where A is any m by n matrix. It's called null space because it's a collection of vectors X that will satisfy this. Okay, this word space here, it's just an alternate word for set or collection. And the word null refers to the fact that it is giving you 0, okay, 0 vector. So if the question says find the null space of a matrix, you are just identifying the free and basic variables, okay, of any m by n matrix A. Do your REF if it is not already done. Okay, sometimes the question gives you the REF, then you don't have to do it again. And then identify the free variables and the basic variables, which all of you hopefully remember from chapter 4. Sorry for all the messy writing here. And once you do that, you could write the solution X by first solving for the basic in terms of the free variables and then writing out the answer in the vector form. So it could be some u times, depending on how many of the free variables you have. Okay, you have some solution where u, v, w are free. And this is what you mean by saying it's a span of vectors for the null space of that matrix. Okay. If we call this as say V1, V2, V3, any particular matrix, then this the vectors that span the null space it's not spanning the matrix A. Okay, so you should be careful about how you communicate these things to another person. There's something called vectors spanning a matrix. It's the vectors that span the solution set of this particular system. Okay, so the vectors that span the null space of A are given by these vectors V1, V2, and V3. Of course, if there is no free variable, then there is no vectors that span the null space. It's just the zero vector. There is nothing interesting. If there are no free variables, that kind of a situation won't arise because there is nothing to do there. Okay, so if you're doing a null space problem, there has to be at least one free variable. But if you're thinking about what if there was none, so if there are no free variables, then x would be equal to 0. Okay, so there is absolutely nothing that spans the null space. So this is something that you should always remember, that it's the presence of free variables that really decides the existence of a non-zero solution for a homogeneous system. Okay, which is what we are going to see when we start doing eigenvalues and eigenvectors. Okay, this is a concept that you have to keep in mind. So if there are free variables, that is a lucky day. That means Ax equal to 0 has infinitely many solutions. Including x equal to 0. That is just one of them, but there are many others. And which automatically means that A is no longer invertible matrix. Okay. Because if it is invertible, that solution would have been unique. Okay. Those are statements you need to kind of go back and forth in the invertible matrix theorem. Okay. So not invertible, which also means that the determinant of A is equal to 0. So these things kind of work in a circular way. Okay, if you spot this, automatically means that if you found the determinant of A, that will be equal to 0. Okay. All right, so that is where we stopped. Any questions about any of these concepts? So if you look at the homework in 5.3, you can see there are several problems that say find the vectors that span the null space of a matrix, or write the homogeneous system or solution to the homogeneous system in the form of vectors. Okay, it all means the same thing. We are just doing what we did in chapter 4, identifying the free and basic variables. So just a repeat exercise for all that stuff. Okay, any questions about any of these? No? Okay, then let's move on to section 5.4, which is a little bit more theoretical stuff again. Chapter 5 is mostly theory before we hit the eigenvalue concept in chapter 6. Pull this up and start clean. So today's lecture comes with a variety of things. You need to just take good notes, okay, unless you want to keep on watching videos when you're writing a test. So write these things carefully so that you don't mistake things that might be important in doing problems. Okay. So this section 5.4, it's about linear independence, which I hope you kind of heard in chapter 2 in the context of differential equations. We always wanted to avoid writing functions and its multiples over and over. Okay, so now we are going to give a more precise and rigorous definition to this. so that it works everywhere, not just for functions. So once again, we are going to live in a world of vectors. So let V equal to V1, V2, V3, dot, 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 Vn be a set of vectors in the vector space V. Okay. So when you write it in a general way, there are n of them, though when we do it by hand, it will be 2 or 3 or 4. Okay. So we say that these vectors are linearly independent sorry for a long line there. Okay. We say that these vectors are linearly independent if the only solution to the homogeneous system C1 V1 plus C2 V2 plus dot 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 plus Cn Bn equal to 0. Okay, so when you take a linear combination and combine them together and try to find what those constants C1, C2, C3, etc. up to Cn would be, okay, if all of them come out to be equal to 0. So the only solution to this is C1 equal to 0, C2 equal to 0, all the way up to Cn equal to 0. Okay. Make sure that you're writing the correct word here, linearly independent, which means that there is no dependency between those variables, okay, which makes sense because there is no way those vectors are related in any fashion. Okay. Which also means that the only solution is the solution x equal to 0, right? There are no free variables. But if there are free variables, or if there's at least one free variable, okay, that is when it just becomes the opposite. So these vectors are linearly dependent if at least one of these scalars would be non-zero. These vectors will be linearly dependent if at least one of C1, C2, C3 dot 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 Cn would be not equal to 0. You don't have to have all of them not equal to 0, at least one of them. Okay. I know it looks like a very technical definition with all kinds of dot dot dots. Okay. Mathematical definitions always look very unattractive because of all these words and notations. But what does it mean? The intuitive meaning is very simple. Or the geometric meaning. Before we start doing crazy things, let's just try to understand what this is trying to tell here. Okay. If you just take your R2 xy plane, just take the vector 1, 2. You don't have to be very creative with that one. Okay. So it just goes from the origin to the point 1, 2, the first quadrant. Okay. And if you take the vector 2, 4, just lies along the same vector. Okay. All you have done is just instead of going 1, 2, you have just traveled twice the distance. Okay. from 0, 0 to 2, 4. And you don't need an advanced degree in math to spot this relationship here. The vector 2, 4 is twice the vector 1, 2. Or if you look surprised. Okay, nothing groundbreaking here, right? So if this is your vector v1 and this is your vector v2, all we are writing is that I don't care how you write this, 2v1 minus v2 equal to 0. And that is what this equation is telling you. You have some kind of a relationship between those two vectors with scalars c1 equal to 2 and c2 equal to negative 1. Now let's take two other vectors. Going to kind of cheat here and take two very convenient vectors, 1, 0 and 0, 1. What do you think about those two vectors? Is there any kind of scalar that would connect the unit vectors along the x and the y axis? Is a scalar multiple of 1, 0 equal to 0, 1? Or the other way around, okay, is c1 times 0, 1 equal to 1, 0. What do you think? First of all, they're sitting at right angles, so pictorially it doesn't make any sense that this is depending on that one. Okay. But if you try to solve this, you get c1 equal to 0. Okay. And if you go along this one, you get 0 equal to 1. So either way, it's nonsense, right? So c1 has to be equal to 0, which means that these are linearly independent. These are linearly dependent because one is twice the other. Okay. So all that is saying is that these are just scalar multiples or non-scalar multiples of each other. Okay. I hope this is nothing surprising again, because that's x-axis, y-axis. If they were related, then we cannot draw any graphs in our applications. Okay. The whole point of having two different axes is because they are two entirely different quantities. So this section is mostly focusing on how to decide if a set of vectors is linearly dependent or independent. So I'll give you a few shortcuts at first, and then there are some places where shortcuts won't work. And that is where it needs some calculations, nothing too heavy. So that's what we'll be focusing on here. Okay. Before I start writing the shortcuts, do you have any questions about the definition of linearly dependent and independent vectors? Shortcuts. I don't know if that spelling is correct, but use carefully or judiciously, which means that don't use it in the wrong place. Okay. Don't force it to happen. If it works and if it applies, good. Otherwise, you just have to do whatever is the alternative procedure. Okay. Shortcut number 1. Visual inspection. If two vectors look linearly dependent or independent, there is no need to use any nuclear weapons to do it. Okay. So just look at the vectors. If, for example, if you have 1, 2, and 2, 4, you don't need any linear algebra to convince somebody that this is twice the other. Okay. So in this case, you could easily conclude one way or the other. And that's what we were doing in chapter 2, right? When you wrote y1 of x equal to e to the power of 3x and y2 of x equal to 5e to the power of 3x, we didn't have to sit here and argue that, oh, how do we know if these are dependent or independent? You can clearly say this is 5 times this, and we move on. Okay. All right, but it's not always going to happen. Okay, when it's there to see, just look and make your decision. Shortcut number 2. If we have, now we need to be careful. Okay, now the more complicated ones come in. If we have m as in mango, okay, m vectors in Rn. This n here, for those of you who have not taken calculus 3, okay, this represents the dimension or tells you how many components there are in that vector. Okay. So R2 will have 2 components, R3 will have 3 components. Maybe it's obvious, but just wanted to tell you this. This is the number of components in the vector. So if there are m vectors in Rn, so if there are say 5 vectors in R3, okay, that's way too many vectors than we need to. And if m is greater than n strictly, okay, it's not greater than or equal to, if m is strictly greater than n, then these vectors are linearly dependent. How do we know that? Well, the reason is that we only need n number of vectors in Rn. Okay, any more than that is just an unnecessary waste of vectors. We are just going to create a relationship where things are just going to depend on each other. Okay, so, for example, if you have say 3 vectors in R2, this is n equal to 2, that is m equal to 3. Okay. And our shortcut is saying that if m is greater than n, we don't need to do any particular test or anything, we can just conclude. The reason is that, for example, if you have 1 0 0 1 and 2 3, the third one is just an arbitrary vector. Okay, I don't care what that is. You can always write this as a linear combination of those two. Okay. 0 plus 3 times 0 1. Okay, so no matter how you do this, there is always going to be that extra vector which is going to spoil the show. Okay. So we don't need any more than the number of vectors or the number of components up here. So that's almost like a visual check. Okay. Though you have to think a little bit, make sure that you're using the right shortcut. If m is greater than n, which means we have more vectors in Rn, those vectors are linearly dependent. So even if the first two are linearly independent, okay, this thing kind of messes it up. All right, shortcut number 3. If the 0 vector is in the set of vectors, okay. Now this is not an easy, difficult one to spot, right? The 0 vector is sitting there, you see it's there. Then the list of vectors is, or the set of vectors, I shouldn't say list, the set of vectors is linearly dependent. Okay. Irrespective of whatever else is going on there. And that's because of the power of 0. Okay. So if you have, for example, v equal to v1, v2, 0, and v3. No matter what v1, v2, and v3 are, we can always write a linear combination of these which are equal to 0. Okay. You can write 0 v1 plus 0 v2 plus 5 times 0 plus 0 v3. That is equal to 0. This 5 could be 15 or 25. Okay. So at least one of the scalars is not 0, So it's a linearly dependent set of vectors. Non-zero scalar here. There's nothing special about 5. You could multiply it by 15 or 151, okay, or 151 square multiplied by 0, you'll get 0. Okay. So even if V1, V2, and V3 are all linearly independent, but 0 vector is the spoiler. 4. No, this is very important. Okay. This is actually a addition to the invertible matrix theorem we have written before. If we have n vectors in Rn, now we have the same letter here and here. Okay. If we have n vectors in Rn, and if the determinant of the matrix A is equal to 0, so this A is written with these vectors as columns, where A is a n by n matrix with the n vectors as n columns. So if the determinant of A is equal to 0, then the vectors are linearly dependent. Okay. Which also means that if the determinant is not equal to 0, they are linearly independent. But you can use this only if you have the same number of vectors as the dimension of that that matrix that you're dealing with. Okay, you cannot have 5 vectors in R3 and take a determinant out of it because it's not square. Okay, it has to be a square situation to do this. So if determinant is not equal to 0, they are linearly independent. We will make use of that quite a bit, not only in this section, also in 5.5. Okay, that is probably the root of everything in linear algebra, the determinant being equal to 0 or not. And it's not very difficult to see why this is the case. Just take the vectors 1, 2, and 2, 4. So A equal to determinant 1, 2, 2, 4. Okay, that is 4 minus 4 equal to 0. Okay, and we don't need this actually, but just to convince you that if you take any determinant with rows or columns being multiples of each other, okay, that is always equal to 0. So an n by n determinant with rows / columns being multiples of each other it's always equal to 0. You don't have to compute it. So if somebody is giving you this determinant here, 1, 2, 3, 4, 5, 6. Okay. If somebody just wants to mess around with you, okay, what's the value of this determinant? And if you spot that this column here is twice this column, okay, you don't have to even bother computing it because it's going to be equal to 0. Okay. I hope I did my multiplication correct. Okay. This is always going to be equal to 0. Okay. And we don't care what else is going on there. And that's because if you have linearly dependent vectors sitting in a determinant, it's going to just collapse that thing into a single plane and there is no volume generated out of it. So those are the shortcuts. But if you observe closely, there is one case that I did not address. What is that case? And this is where you have to be careful. Okay. If you go through shortcuts 1 to 5, we'll do some examples. So how many did I write? 1, 2, 4 or 5? 4. There is one particular case which I did not address. Which case is that? M is less than n. Okay, so be careful here. So there is no shortcut if we have m vectors in Rn, and if m is less than n. Okay, we have shortcut number, I forgot the numbers, I think it was shortcut number 2 if m was greater than n. Okay, shortcut number 4 if m is equal to n. This one we didn't find anything. Okay, this is the only case where you have to set up a linear system and really solve for it. Okay. Unfortunately, if m is less than n, set up the homogeneous system. Don't forget, this is always consistent. Okay, set up the homogeneous system. C1v1 plus C2v2. How many other vectors there are? Okay, plus Cnvn equal to 0. Do the REF if necessary. And identify the basic and free variables. First of all, the immediate check is, are there free variables? Again, I'm talking about a case where it's not visually obvious that is are linearly dependent or not. Okay. So the question is, are there free variables? If the answer is yes, the vectors are linearly dependent, because then you can write a linear combination that connects those vectors. If there are no free variables, then they are linearly independent, which means all the variables are basic here. And since we are dealing with the uneven matrix, we cannot talk about invertible or not. Okay, that is not a question that you can ask in that particular context because it's a non-square matrix. But if there is any work you have to do in 5.4, it is in those problems where you have fewer vectors than the dimension and it's not obvious as to what is going on. Okay, so let's spend most of today's lecture trying to get this right. Okay? So some of these could be just easily done. Some of this you have to do it. So before I erase all these things one by one, do you have any questions about any of these as to why? I'm not proving any theorems here. Okay, that is not the purpose of this class. But if you have any questions, I can clarify with an example. I can do it now. Any questions? Okay, so let's see if you have written your shortcuts correctly. Okay, so here are some questions. The question is, are these vectors linearly dependent or independent? Okay. For now, just answer that part. We're not really finding the linear combination. We'll do that later. Okay. Are these following vectors linearly dependent or independent? Just going to use D, P, and IND for just to shorten my writing. First one, 3, 4, 7, 4, 1, 2, 5, 3, 8, 6, 1, 9. What do you think? Are these vectors linearly dependent or independent? Yes. Dependent. Dependent. And which shortcut are we using? 2. So we have 4 vectors in R3. R3 because yet there's 3 components. Okay. So m equal to 4 greater than 3 vectors in R3. And that means please don't set up a determinant. Okay. It's a non-square situation. So these vectors are linearly dependent. This is how you save time on tests that involve these kinds of questions. You don't want to sit down and waste time trying to solve it by, if you try to solve it, you will get some free variables. Okay, but this is a yes or no question. So just do that and move on. Okay. What about this one? This might be a little obvious, but you never know. Online people, what do you think? Maybe it's a silly question to ask today. Maybe tomorrow it might be. What do you think? Are these vectors linearly dependent or independent? Dependent because of the pi and the e, or what's the reason? The zeros. Okay, so this is the bad apple there, sort of. Right? So these are linearly dependent because the 0 vector is there. In this case, you can even find the determinant. The 0 columns would just kill it. Number 3. Now, this is a slightly tricky one if you don't pay attention to carefully. So these are actually 3 vectors in R4. Okay, so none of the shortcuts apply as such. So this is 1, 2, 3 vectors in 1, 2, 3, 4. So m equal to 3 vectors in R4. Unfortunately, shortcut number 2 is not a flip-flop statement. Okay, it only applies one way. But is there something in that set of vectors that kind of tells you some obvious stories? Yeah, the third vector is the sum of the first 2. Okay, so if you name this as v1, v2, you should be able to just look at the vectors and say, oh, 2 plus 4 is 6. You all know that. Okay. And similarly, all the rows, I think they add up to the third vector. So v1 plus v2 is v3. It's kind of a visual inspection in this case. Okay. So they are linearly dependent. Any questions so far? So I think I've kind of mixed up the different shortcuts I've written. Okay, here comes the more important one. Now pay attention. Number 4, find the value of k so that the vectors two, 1, k, 3, 0, 2, 5, 7, 1, negative 3, 2, 4, and 0, 4. I'm just making up some numbers. Hopefully they'll work out okay. So find the value of k so that these vectors are linearly dependent in R4. Okay. The R4 part is kind of obvious because it's sitting with 4 components. Okay. So these are the kinds of problems I want you to be kind of, it doesn't really tell you what to do, right? But maybe today you know what to do because I just wrote down the shortcuts there. Okay. So what do you think you should do? So if I count it right, there are 1, 2, 3, 4 vectors in R4. What is our strategy here? In any problem like this, I mean, there has to be a way to do it, right? Unless you want to plug in each value of k and test it out, you don't want to do that. So what has to be the way or the method here? Yeah. Find the determinant and what is the find the determinant and there should be, if you find the determinant, it's going to give you something in terms of k, right? And set it equal to I mean that's only special number we know, right? 0. Yeah. So set the determinant equal to 0 because that is what shortcut number 4 told you. I could be wrong with the shortcut numbers here. Set the determinant equal to 0. Okay, so these are alternate ways in which you could be asked to evaluate determinants. Okay, this is a 4x4 determinant, for example. So let's write the determinant and I'll wait for you to do this yourself using whichever row or column of your choice. I would suggest that you don't try to triangularize situations like this because it may not work out nicely. Okay, it will give a correct answer, but maybe a pain in the where. 1, -3. So why don't you take your time and solve it slowly? It's also a good practice for the test. All right, so I'm going to expand it along the first row. Okay. If you didn't get a chance to do determinants by hand, please do it in the next couple of days. Okay, don't wait till the day of the test. It looks easy when somebody else is doing it. So this is 2 times the 3 by 3 minor. That's going to be 2, negative 3, 4, 5, 2, 1, 7, 4, 3. Minus 0 times whatever, okay, plus 1 times it's 3 by 3 minor, which is going to be kind of drew through that, but it's 1, 2, 4, K, 2, 1. No, K5, 1. 1, 2, 4, K5, 1, 3, 7, 3. And we are setting this equal to 0 because we want to see what value of K would make these vectors linearly dependent. Okay, if it is independent, it will be not equal to 0. So just read the question. Okay. All right, so I'm going to just do the 3 by 3s using the first row. Okay, that's 2 times the first 3 by 3, which is 2 times 2, 1, 4, 3, minus negative 3, it's plus 3 times its minor, 5, 2, 5, 1, 7, 3, plus 4 times, if I'm not writing this properly, 7, 4. So those big brackets are for this 2 outside, just so that I won't forget it, plus 1 times, that's okay, 5, 1, 7, 3. Minus 2 times K1, 3, 3. You could have expanded it using any row or column. Okay, so if you did something else, you don't have to correct it. K5, 3, 7. Okay, let's clean up these 2 by 2s. This is going to be 6 minus 4, that is 2. This is 15 minus 7, which is 8. This is 20 minus 14, which is 6. So altogether we have 4 plus 24, 28 plus 24, which is 52 times 2, which is 104. That is including this 2. And let's come here. This is going to be 15 minus 7, which is 8. This is 3K minus 3. And that will be negative 6K plus 6. If you multiply the negative 2. And this is 7K minus 15. And the product of this 4 and this pair of terms would be 28K. That is a plus 28K minus 60. And since I wrote these numbers randomly, may not give you a clean answer, that's okay. So we have 104, 112. Then you have plus 22K minus 54. So 22k is negative 58. So k is negative 29 over 11. Is that what you got? Somebody, yeah. Be very unlikely if 2 or 3 of us get the same wrong answer of that kind. So hopefully, if 2 people get it right, that's a good sign. Yeah, it's very easy to make small mistakes here with all the positive, negative alterations. So be careful. Okay. So that is whenever you see this, find the value of k. Just think about determinants. That is usually the way out. Any questions about this? All right, now let's do the one where we have to do some computations. Okay, so just looking for a good example from the book, because it's very difficult to find these problems. You have to make it up nicely so that it gives you nice numbers. So I'll pick a couple of questions from the exercises. This hopefully is not in your homework. Okay. So example 4, 5. All right, so are the following vectors, and just ignore the fact that these are in your homework. Do it again when you do the homework. Okay. Are the following vectors linearly dependent or independent? If linearly dependent, write a linear combination which vanishes. And before I write the question, this anybody understand what this word mean in a mathematical context? Vanish. If I was a magician, I could probably make things vanish. But when you do this problem, what exactly does it mean by saying write a linear combination that vanishes? What could be the equivalent of vanish in mathematics? Yeah, just equal to 0. Okay. A linear combination equal to 0 is what it means by saying it vanishes. So you don't have to sit there and think about how to do impossible things. Yeah. All right, so the vectors for this particular question are v1 equal to, wrong notation, 2, -4, 6, and v2 equal to -5, -10, -15. Sorry, -5, +10, -15. Sorry. Right. Some of you might be able to look and say, oh, I already see a relationship, but it's not very obvious. Okay. So the question is, are these dependent or independent? And usually when the second part of the question says this, okay, usually that means they are linearly dependent, because otherwise there is no point of asking that. Okay. So maybe we have some kind of a hint already in the question. First things first, you cannot apply any shortcuts here. Okay. There is no determinant you can make out of this. These are 2 vectors, 3 rows. So these are actually m equal to 2 vectors in R3. Okay, so when m is less than n, no shortcut. Okay. That's the first thing you should do so that it doesn't become a disaster just in an instant. You cannot just say, oh, these are linearly independent because the other statements are dependent, so this must be the opposite. It's not. Okay. All right, then what do? You set up the homogeneous system. So C1 times 2, negative 4, 6, plus C2 times 5, negative 5, 10, negative 15, equal to the 0 vector in R3, which is 0, 0, 0. That is what we are trying to solve here. And our investigation is to see if both C1 and C2 are equal to 0, or if at least one of them is not 0. So unlike the span question, there is no consistency issue here. Okay. All we are looking at is, are there free variables or not? It's always consistent because the right answer is 0. All right, so let's write you don't have to write an augmented matrix here because it's homogeneous. Okay, so just write the matrix with the 2 columns, 2, negative 4, 6, and negative 5, 10, negative 15. I know it's very tempting to divide the first row by 2. Let's try to take care of the second and third rows first, and then we can come back to the first row. Okay, because it's a 2, why don't we just take care of this negative 4 and 6? It's your choice. But R2 plus 2R1 and R3 minus 3R1. 2, negative 5. R2 plus 2R1 will give you 0, 0. And R3 minus 3R1 gives you the same result, 0, 0. So the rank of that matrix is just 1, okay, because there are the 2 rows full of zeros here. Now you can, if you want, divide the first row by 2, though it's kind of pretty obvious as to what's going on here. Okay, so 1/2 R1. If you are very religious about REF, 1, negative 1/2, 0, 0, 0, 0. So there is C1 in this case, not X1. C1 is basic, C2 is free because there is no leading one in the second column. Okay. So as soon as you find that there is one free variable, the answer is that they are linearly dependent. Okay. So V1 and V2 are so the yes or no question is based on the presence or the absence of free variables. Now the question is, okay, then what is the relationship between those variables, okay, or those vectors? Well, make use of this. So this gives you, let's call C2 as U, or whatever letter you want to use, because it's a free variable. Okay. So you have C1 minus 5/2 C2 is minus 5/2 times U equal to 0. And that gives you C1 equal to 5/2 U. Remember that U is a free variable. Okay, give some value for U, whatever you like. Preferably not give U equal to 0 because that's kind of a boring case. Okay, give any non-zero value for U. Remember that mathematics doesn't give you a lot of options like this all the time. Okay, usually math is kind of very uptight about what should be done. In this case, it's a free variable. That's why you can do whatever you want. So my choice is U equal to 2, so that I don't have to deal with fractions, but it's your choice. Okay, say U equal to 2, and that will give you C1 equal to 5. And since C2 is U, I have C2 equal to 2. Okay, but you can have other answers, right? If you have u equal to 15, then C1 and C2 would be correspondingly scaled. Okay. So the linear combination that vanishes in this case would be C1, which is 5V1. So just to illustrate that this is actually true, I'm just going to write V1 down here. 5 times 2 negative 4 6 plus 2 times negative 5 10 negative 15. So if you just multiply each of them and add them together, you have 5 times 2 10 minus 10 is 0, negative 20 plus 20 is 0, 30 minus 30 is 0. Okay. So this is indeed equal to the 0 vector. And that is what it means by saying it vanishes. Okay, in this case, a linear combination of these two vectors equal to 0. But you can have other answers here. You could have 10 times the first vector plus 4 times second vector. Okay, that is what is going on here. So any scalar multiple of this is going to be an answer. You don't have to pick u equal to 2. You could pick u equal to 1, u equal to 5, u equal to 15, okay. U equal to pi, whatever you like. All right, any questions on this one? I know it's a pretty mild example because you only had two vectors. Okay, once you get the idea, now you should be able to do it for any number of vectors. Any questions on this? All right, then let me ask you to do the next one. Things get easier by the day. This is getting harder and harder. Okay. I'm going to give you a bigger set here so that you have some time to work on. Okay. Oops. All right, let me find that list. What to say? Okay, here we go. V1 equal to 1 0 1 2. V2 equal to 2 0 4 8. V3 equal to 3 2 1 0. V4 equal to 4 0 0 0. And V5, so you probably know the answer, whether it's linearly dependent or not. Okay. V5 equal to 5 4 3 2. These are obviously linearly dependent because you have 5 vectors in R4. Okay, so I can just ask the question, are these linearly dependent? Okay, but more importantly, I wanted to answer this part. Write a linear combination that vanishes. So take some time, set up the homogeneous system. Okay. Actually, find an null space of that matrix. Okay, so that is the matrix with the vectors as columns, and then you can do your routine operations. Oh, you can also divide the second row by 2. I don't know, can somebody verify those for me? Kind of look okayish. At least I like how they look. Got a lot of even numbers in the last 2 rows, so I don't want to miss that, but are they okay? Appearance wise. Depends on which order you did it to. Okay, but all right, good. So there's one confirmation. Let's move on. 1/2 R3 and 1/2 R4. Some point we might have to swap some rows, but 0, 181. And R4 minus 2 R3. Maybe it's a bad idea to squish it in there. Me. One, 2, 3, 4, 5. Which one? It's 2 R3. Okay. So what I'll do now is to add R4 plus R2 and also swap R3 and R2. If you spot any mistakes, please feel free to unmute and shout out. Okay. So 1, 2, 5, 0, 1, -1, -2, -1. Yeah, that looks okay-ish. Well, it's not a unique form because this is not an RREF. Okay, you could still do more things, but I think for our purposes, this should be enough to keep moving. So the leading ones of each row are sitting here, here, and here. The last row is just a row full of zeros. Okay. So this example is kind of answering a lot of different kinds of problems. Okay, it's also finding the null space of the matrix, also checking if the vectors are linearly dependent, which they are, okay, because you have too many vectors. And it's also helping you write those three vectors as a linear combination of the remaining two. Okay, so x4 equal to u is free, and x5 equal to v is also free. Okay. So it kind of agrees in multiple ways that you had more vectors than needed, and you have free variables. Okay, all points towards the same fact that these are linearly dependent vectors. Now let's start solving it. So row 3 gives you so it's x. We're using C1, C2, C3, C4, C5. So it's 0 C1 plus 0 C2 plus C3 plus 2, just to be consistent with my notations. Okay, I don't mind if you write x5, but plus 2v equal to 0. So C3 is -2v. Now it gets uglier because we did not spend time writing it in RREF, so all those rows are sitting in their actual form. Okay, so it is C2 minus C3, that is going to be minus -2v, minus 2C4, that is minus 2u, minus v equal to 0. Don't forget we are solving homogeneous system here. Okay. So C2 is 2u, and then you have minus v. Okay, this is plus 2v minus v. So when you shift it over here, it becomes minus v. And the worst of them all is row 1, which gives you C1 plus 2C2, which is plus 2 times 2u minus v, plus 3c3, that is going to be plus 3 times -2v, plus 4 times u, plus 5 times v, equal to 0. So C1, we're just doing Gaussian elimination backwards. So first we got C3, then C2, now C1. And C1 is, you have a 4u here, a 4u there. That's going to be -8u on the other side. And then you have some v terms. That's 5 minus 6 is -1, minus 2 is -3, becomes a plus 3. Let me know if you're getting different numbers there, because it's possible that I messed up some sign. Can I get a confirmation of some kind? Yeah. All right, now let's write the answer in a more organized way. Remember that you have to write a linear combination at the end of this, so you cannot just leave it like that. So C1, C2, C3, C4, C5. equal to your typical vector form, that's u times -8 2. C3 has no u terms, C4 has 1u, C5 has no u. Plus v times 3 -1 C3 is -2, C4 is 0, and C5 is 1. There are two free variables here, so just do something that will give you some meaningful answers. Okay, we got multiple levels of freedom here. So as long as you don't set both u and v equal to 0, okay, that is good. So set uv equal to any numbers of your choice, including one of them equal to 0, if you just want to make it easier for you. Okay. Don't set u equal to 0 and v equal to 0. That's just telling you 0 equal to 0. Okay. So I'm just going to go with u equal to 1 and v equal to 0. Okay. You could do u equal to 0 and v equal to 1. That is, these are all possible linear combinations. So in this case, you'll get C1 equal to -8, C2 equal to 2, C3 equal to 0, C4 equal to 1, and C5 equal to 0. Okay. But if you picked u equal to 0 and v equal to 1, you would have C1 equal to 3, C2 equal to -1. All these are answers. So you can also pick u equal to 0, v equal to 1, or if you are really in a mood to give non-zero numbers everything, you can put u equal to 1, v equal to 1, and so on. All these are or, not and. So let me just stick with what I decided here, and that will give you -8v1 plus 2v2 plus 0v3 plus 1v4 equal to 0. That is a non-zero linear combination that vanishes. So there are multiple answers possible here. And this is the idea that we'll be using when we do eigenvectors later. Okay, this idea of assigning non-zero cases to free variables like this without generating zero vectors. Okay, I think that's a pretty comprehensive example of what you could see in most of the 5.4 examples where you need computation. Okay. Can't get worse than this. 5 vectors in R4. All right. One last topic. We should be done. Remember back in chapter 2, we kind of took some things for granted, right? There used to be a time when we were talking about differential equations and solutions in the semester. Okay. In particular, we used to make statements like this: e to the power of r1x and e to the power of, so y1 equal to this, y2 equal to e to the power of r2x are linearly independent functions. Okay. And we didn't have any problems with it because that makes sense. These are completely different functions if r1 is not equal to r2. That was based on a faith, right? I mean, you just believed that it was a pair of linearly independent functions. There is nothing to doubt as long as r1 and r2 are different. But how do we kind of convince ourselves that that is indeed true? Because these functions are pretty crazy things. You know, just we just met them a few years ago, but they have a life of their own. Okay, so we need to be careful about making these statements. So the question is, how can we determine if a set of functions we are back to the functions that you were doing in calculus. Okay, these are all vectors in an abstract sense. So set of functions f1 of x, f2 of x, dot fn of x are linearly dependent or independent. Can we do something mathematically concrete so that we don't have to trust on people's instincts and beliefs? Okay, that's the question. Well, based on what we have just done, if these are vectors, what we can do is we can write c1 times f1 of x plus c2 times f2 of x plus cn times fn of x equal to 0. And the question is, what is c1, c2, c3, and so on? Because that's what you did earlier, right? Anytime you have linearly dependent, independent situation, this is where we start. There's only one problem. We have n variables and just one equation. Okay. One option is you could say, well, I cannot solve this and move on. Okay, but one person did not do that. Okay. Luckily for us, he did something which could be used for the rest of whatever differential equations we were doing forever. Okay, his name was Wronskian. You may have seen his name in chapter 2 if you kind of glanced over sections 2.1 and 2.2. Okay. I didn't do it back then because it wouldn't make any sense. Why would this even be true? Okay. So what Wronskian did was, it took this equation and just take the derivative of this from left to right, assuming that these functions are all differentiable. Okay. Or n times differentiable. Which means you could take the first derivative, second derivative, third derivative, and so on. Okay. So they're all well-behaved functions, polynomials, exponential, sine, cosine. So take the derivative of this equation from left to right, you get c1 times f1 prime of x plus c2 times f2 prime of x plus cn times fn prime of x equal to 0. Okay. He made it slightly better there, right? N variables and two equations now. Then he had a crazy idea, just keep doing this. Okay. Just keep doing this till you have enough number of equations to solve the system. So that's why I insisted on n times differentiable so that you could keep on taking derivatives. So c1 times f1 double prime of x plus c2 times f2 double prime of x plus cn times fn double prime of x equal to 0. Okay, that's a third equation. And dot 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 dot. We need an nth equation at the end so that we have a full solvable system. Okay. So keep on taking derivatives. And the nth equation if you look at the pattern, the first equation had the 0th derivative, the second equation had the first derivative, third equation had the second derivative. It's always one less. Okay. So the nth equation will have the n minus 1th derivative. I'm going to write like this because that is the only way we could use that notation. Okay, this within parentheses plus c2 times f n minus 2 n minus 1 f2 of x and so on up to c n f n minus 1th derivative of the nth function x equal to 0. Now we have n variables and n equations. We have an n by n system now. Okay. Not only that, Wronskian observed that now we can build a determinant and make use of shortcut number 4. Okay. So using shortcut number 4, can create a determinant of all the terms that are multiplying this C1, C2, C3, and so on. Okay, so it's going to look like this: F1, F2, F3, dot 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 Fn in the first row, F1 prime, F2 prime, Fn prime, and keep writing this one row at a time. The second derivative will be the third row, third derivative will be the fourth row, and so on. Okay. Set this determinant equal to 0, and then just like the vectors are linearly dependent, the functions are linearly dependent. Okay. Fn are linearly dependent. So he had his kind of mark in the history of math. Okay. This determinant is called the Wronskian determinant. It's a small discovery, but it's extremely useful when it comes to solving differential equations, but because it gives you a pretty concrete guarantee that these functions are usable without doubting about they're linearly dependent or not. So if the determinant of this particular thing is equal to 0, then they are linearly dependent. If not equal to 0, for at least one value of x, then they are linearly independent. Okay. That's the only place where Wronskian has to be done carefully, because it is not saying that it has to be not equal to 0 everywhere. Okay, it could be not equal to 0 at some points. That's okay, as long as it's not equal to 0 for at least one value of x, we are good. Okay, so be careful about what the statement of Wronskian is telling you. It does not help you in finding the linear relationship or anything. Okay, it's a very bare bones kind of is this or not kind of situation. Okay, if this determinant is 0, dependent; not 0, not dependent. That's it. Okay. It cannot tell you any further stories about the functions, how are they related, or what kind of functions they are. That is not Wronski's business. And since we'll be doing mostly 2 or 3 functions at a time, okay, let me just write down the special cases. So for F1 and F2, the Wronskian W of F1, F2 is the determinant whose first row is just F1, F2, the second row is F1 prime, F2 prime. These are functions of x. I'm not explicitly writing it out. And for 3 functions, F1, F2, F3, Wronskian is F1, F2, F3, F1 prime, F2 prime, F3 prime, and F1 double prime, F2 double prime, F3 double prime. Those are the 2 cases that we'll be mostly doing. We won't be doing anything beyond 2 or 3 functions. Okay, so if you can do one of these, that should be good. Don't forget how to find derivatives. Okay, that is one of the requirements of Wronskian, and that's probably the only place we're going to use calculus in this particular test or this chapter. So I'll do one example today and conclude today's lecture. So example, use Wronskian to check if the functions 1, x, and x squared are linearly dependent or independent. Maybe you already know the answer. They don't look like they are scalar multiples of each other. Okay, but let's make use of Wronskian and make sure that it is indeed the case. So those are your F1, F2, F3. In this case, the first row would be 1, x, and x squared. Okay. Now the derivative, I'm not going to ask you what the derivatives of those functions are. It's pretty embarrassing. It's 0, 1, and 2x. And the second derivatives are 0, 0, and 2. So it's a 3 by 3 determinant. You can just use the first column to expand it if you want. Okay. So expand it on the first column, and you get 1 times 1, 2x, 0, 2, which is equal to 2. Not equal to 0. And by the conclusion of the result of Wronskian, okay, if it's not equal to 0, this is not equal to 0 everywhere, okay, but in particular, at least for one value of x, it's not equal to 0. So these functions are linearly independent. Not promising that all the derivatives will come out to be this easy, but this is the concept. Okay. All right, so up to here for Thursday's test. I'll do maybe 1 or 2 examples more with Wronskian tomorrow. Okay, but make sure that you practice the problems in 5.3 and 5.4. Tomorrow I'll just go through anything that you have questions about, okay, and then do 5.5. So that's it for today. Please do your homework without falling behind. Okay. All right, thank you.
Thank you.
Stop recording.